Last time we have introduced how we calculate the moment of a force, okay? And we will see that we can calculate the moment of a force by another way, which is the vectorial method. So we learned some operations that we can apply on vectors, and today we will continue, okay? So as we said, in general, when we want to calculate moment of forces, and we want to use the following rules that we will see in this slide, we should take a right-handed coordinate system. And to determine if it's a right-handed coordinate system, we use the right-hand rule. Okay. So here, as you can see, we put our right hand fingers along X and we curl them towards Y. The thumb will point upward into K direction. Now, if you want to do in this case, if you want to do I vectorial J, using the 3 fingers, we can put, so as we said, or we use the 4 fingers, we curl them from I to J, the sum will give us K. The second method, we can use the 3 fingers. First, the thumb along I, the second finger along Y, the third finger will be pointing upward along K. So we will say that in this case, because it's a right-handed coordinate, I can say that I vectorial J will give me in direction plus K. And of course, in magnitude, I vectorial J, the magnitude of I vectorial J is magnitude of I times magnitude of J times sine the angle between them. And we know that here it's a rectangular coordinate, so the angle between I, J, K is 90 degrees. So it's 1. This is why we can say that I vectorial J is equal to plus K. Now, if we do, for example, I vectorial I will give us 0, because the angle between I and I is 0, and sine of 0 will be 0. Now, for example, if you want to do J vectorial I, we apply the same rule, but now we put our right hand first along J and we curl it towards I, then our thumb will point in the opposite direction. So it's equal to minus K, okay? Now, if you don't want to use the right-hand rule each time, you have a simple method that will allow you to calculate the vectorial product. What you can do is, you can draw the following circle. So you have this circle here. You choose a positive direction, and you draw I followed by J followed by K. And the positive here is from I to J to K is the counterclockwise direction. So if I do I vectorial J, I am turning in the positive direction, it will give me plus K. If I do K vectorial J, for example, I am turning in the negative direction, it will give me minus I, okay? And I can do it also in my hand, in my head. So I say I, J, K, I, J, K. If I'm turning in this positive direction, I, J will give me plus K. If I do K, I, it's also in the positive, K, I, J, J, K, I, so it's plus J. If I do the opposite, J vectorial K, so I'm not, I'm turning also in positive, so I. Ji is not in the order because the positive order is ijk. If I do j vectorial I, so it is minus. So you can use any method that is convenient for you, or you draw the circle, or you use the right hand rule, or you just say the order I, j, k, I. If you are going in the positive order, it's plus. If you are going in the negative order, it's minus. So this will give you all of this information. So k vectorial k 0, j vectorial k, I'm turning in the positive direction, so plus I, etc. Okay? Now, in general, another way to calculate the vectorial product is the analytical way. Okay? So if I have two vectors, A and B, and I am doing A vectorial B, I can decompose A and B into their components. So I will write A in the form of AXI plus AYJ plus AZK. And the same for B, BXI plus BYJ plus BZK. And we have learned from operation on vectors some rules. So here, if you want to do this vectorial product, you will expand. It's like we have numbers. So we start doing AXI vectorial BXI. But I vectorial I is 0. So the first term will cancel out. Plus AXBY times I vectorial J. I vectorial J, so I'm turning in positive direction, IJ, so I get plus K. So the first term will be this one, AYBY times K. Now if I continue, I have I vectorial K, it's in the negative direction because the positive one is K vectorial I. Okay, IJKI. So I vectorial K is minus J. So it's minus AXBZJ. As you can see here, you have the term here, minus AXBZJ. If I continue to do my expansion, okay, I do all the terms and then I group I components together, J components together, and K components together. I get this final result. That C is AYBZ minus AZBY along I, minus AXBZ minus AZBX along J, and plus AXBY minus AYBX along K. It's hard to remember this, okay? So instead of memorizing this formula, we have a method to simplify the vectorial product, which is the matrix method, okay? What we do is, we want to obtain this result using a simple way. So according to this result, we have developed the following way to calculate it in a simple method. So what we do is we draw a matrix. For the first line, we put vectors I, J, K. For the second line, we put the components of vector A, AX, AY, AZ. For the third line, we put the components of vector B, BX, BY, BZ. And now, to calculate the vectorial product, what we do is the following. We put the plus sign above I, the minus sign above J, and the positive sign above K. And now we say, first, I want to determine what is the component along plus I, okay, along plus I. So what I do to do this, I will drop the column of I and the line of I, and then I still have 4 numbers here, okay. So first, along plus I do the following. I multiply this term by this term minus this term by this term. So it's AYBZ minus BYAZ. As you can see, it's the same term here. Now, once I'm done with this one, I move to minus J. So because I have above J, I have a minus. So now I want to know what is the component above minus J. So what I will do, I will drop the line of J and the column of J. And I still have the following 4 numbers. So I will do AXBZ minus BXAZ times, of course, minus J. So as you can see, I can obtain the second term here. And at the end for K, the final term is plus K. So it's plus K here. I drop the line of K, the column of K, and the remaining numbers are the following one. So I do AXBY minus BXAY times K, and this is the result here. So no need to memorize this. We can just apply the matrix method. Now, sometimes the numbers are very simple. So for example, if you have 2I vectorial 3J, for example, plus 2K. No need to do the matrix because here you have the number of terms is very small. You can directly do the expansion. So you do I vectorial j is plus k. So 2 times 3 is 6. So this is 6k. And 2i vectorial k. I vectorial k is minus j. So it is minus 4j. So here it's much easier to do the expansion instead of the matrix. If you have a lot of terms, it's easier to do the matrix. Of course, here the matrix will give us the same result, but here it's fast. Let us do the matrix for this simple example. If you want to do the matrix for this simple example, you do this. So, as we said, the first line is ijk. So I put here ijk. And now, the first line is the components of the first vector. The first vector is 2i, so it's 2, 0, 0. And the third vector is, the second vector is 3j plus 2k. So it's 0 along I, 3 along j, and 2 along k. And now you start. Okay, first you want to find the component along positive I. So what you do along positive I, you drop these this column and this line. So you have 0 minus 0. So it's 0 along I. So the first component is 0 along I. Now along minus j, okay, to find the, always do not forget to put always the minus above j. So along minus j, what do I have? I drop here this column and this line. The numbers are 2 times 2, which is 4 minus 0. So it's minus 4j. So the second term is minus 4j. And the final term along k, I will drop these two. So I get 2 times this 3 minus 0, which is 6. So plus 6k. And of course, I will get the same result. Okay. So plus 6k. Okay. Any question until here? Okay. So now we will see how to relate the vectorial product to the moment of a force. What is the relation between them? In general, in 2-dimension, I don't need to use the vectorial product because we have developed together a simple method, which is to find the projected distance and to do the right-hand rule for the direction. But in 3D, the issue is much more complex. In 3-dimension, it's not easy to find the projected distance due to complication of geometry. Okay. And your moment can be along any direction. It can be different than ijk. This is why we define a second method to find the moment of a force, which is according to the vectorial formulation. What is the formula we will use? We will demonstrate together that the moment can be written as follows. It is equal to r vectorial f. Now, what is r and what is f? Of course, f is the force. So let us say I want to find the moment of vector f about point O. Okay? Then the technique we use in general is to draw the perpendicular. In 2D, the technique was to draw the perpendicular to f and to say that the magnitude is the distance times f, and for the direction we use the right-hand rule. So if we use the right-hand rule here, it will be like this. It will rotate in this way, as you can see in the arrow. But for 3D, we'll develop a general relation. What is the relation? First, r is the position vector from the point about which I want to do the moment. So if I want to do some of moment about O, the origin of the position vector is O. And A is any point of application of the force. We will see that wherever is the point A I take, when I do R vectorial F, I will get the same result, and we will see why. Okay? Because if you look at your figure here, if I take this vector r, okay, and it's doing any angle, an arbitrary angle with the line of action here, it's not by force 90, so any angle theta, okay. If I want to find the magnitude of r vectorial f, what is the magnitude of r vectorial f from definition? For the cross product, the magnitude of r vectorial f is the magnitude of r times the magnitude of f times sine of the angle between them. So times sine of theta, okay? But if you look at this figure here, what is r sine theta? It's equal to what? If I do r sine theta, I will get the projected distance d, okay? So whatever is r sine theta will always give me d. So for example, if I take r as following, if I take the vector r like this, what will change? Theta will change and r will change. But when I do r sine theta, I will always get d, okay? So in both triangles, r sine theta will give me the projected distance, the perpendicular distance d. So I can say that this term is nothing than d, which is the projected distance from O on the line of action of the force. So until now, when I did r vectorial f, I got the magnitude of the moment. Now I still should verify the direction, okay? So when you do r vectorial f, from the right hand rule, okay, if you go, I posted for you several YouTube links on the right hand rule, okay? When we do r vectorial f, the technique is we take our right hand, we put the 4 fingers along r, and then we curl our hand. So try to do it now. If you put your 4 fingers of the right hand along r, except your thumb, okay, and you curl your right hand towards f, your thumb will point in the upward direction. So you can say that r vectorial f will give me a vector that is perpendicular to the plane of r and f, and that is in the upward direction, which verifies the moment direction, because the moment is found from the right hand rule, and the vectorial product is given also in direction by the right hand rule. So from this method, when I do r vectorial f, I am obtaining the same characteristics of the moment in magnitude and in direction. This is why a general way to find the moment of a vector about a point is to take r vectorial f, where r is the position vector from O towards the line of action of the force, and f is the force. Any question on this? Okay, so as you can see here, this is what we said, okay? First, for the magnitude, we have r sine theta is equal always to d. And if you can see here, it's your right hand, okay? This is how you apply it. Look, you take your 4 fingers along r and you curl them towards f. Your thumb will point in the direction of the moment. Now, in this way, okay, to calculate the moment, I can use the analytical method, because we have seen together that if I have 2 vectors A vectorial B, I can calculate the vectorial product analytically. So, first, I will put the matrix, put I, J, K in the first line. The second line represents the components of vector position r, so I put rx, ry, rz. And the third line is the components of vector f, fx, fy, fz. And now, applying the rule we have developed together, we can calculate the moment of any force about O. And of course, if you have several forces and you want to do the resultant moment, you should do the summation of moment of each force about O. Let us do a small example together to see how to apply this. So we have given the rectangular plate that is hinged at A and B and supported by a cable which passes over a frictionless hook at E. The tension in the cable is 1349 Newton. Find the moment about coordinate axis of the force exerted by the cable at C. So, when they asked for a moment about axis, you will see that when you do moment about a point, okay, you will obtain a vector. And this vector represents what? So, for example, if I calculate the moment, okay, when I calculate MO as a vector, what I will get? I will get three components, one along x, so MOXI plus MOYJ plus MOZK. Okay? Now, when I get this vector, what does these three components mean? MOX represents the moment of my force about x-axis. MOY represents the moment about y-axis, and MOZ represents the moment about k. In 2D, we don't have this y because in 2D, the moment is always, if we have ij, if all my forces are in ij plane, in 2D, my moment will be always along z. This is why in 2D, we don't put it as a vector, we just put MO, because MO in 2D is restricted to MOZ, okay? But in 3D, you cannot do this because your moment can be in several, can have component in different directions, okay? So in 3D, it's more complex. My moment can be decomposed into I, J, and K components. So when they ask you, they are asking you here to find the moment about the coordinate axis. So they mean by this small x, small y, small z. And small x, small y, small z are passing all by point O. So it is like they are asking you, what is the moment of the force about O? Okay? So now, the second step is to write the moment in a vectorial form. They want us to find the moment of the tension force, okay, about a point. So to do this, first, the tension force passing at C, as I said, okay? So here I have a cable. The tension in this cable is, it's applied on the plate, so it's pulling it. This tension is pulling it upward here, and the tension is pulling the plate here also upward. But they are interested in the force applied at C, okay? So what is the position vector here I can take? The position vector from O to any point on the line of action of your force, okay? So your force here is passing by 2 points, C and E. So I will call it TC, TCE, okay? So we can say that the moment of O, the moment of TCE about O can be written in two ways. I can take R, I have two options for R. Or I take OC, or I take OE. Because we said that the position vector is directed from the point about which I want to do the moment towards any point on the line of action of C. So I can take OC vectorial TCE, or the second option, it will be equal also if I take OE vectorial TCE. So I can take any point on the line of action of the force. Any point will work, as we demonstrated. So you will choose the easiest point, okay? So for example, here C is on Z axis. So the coordinates of C are much simpler than the coordinates of E, because E has two components, while C has only a component along Z. This is why I will choose OC vectorial TCE. but you can do it as a practice. Try to do also OE vectorial TCE, and you will see that you will get exactly the same result. So here, I will replace each vector by its term. So it's equal to, for OC, it is, as you can see in the figure, it's 2.25K. So it's 2.25K vectorial TCE. Now, what is vector TCE? By definition, vector TCE is magnitude of TCE times unit vector of CE. So the magnitude is given, it's given here, so I will replace it by its value, 1349 Newton, times what? Times unit vector of CE. Okay? And now to find the unit vector of CE, it's very simple. All I have to do is to find the coordinates of C and E. For C, I already know that it is 2.25K. For E, if I look at my figure, okay, E has components only along Y and X. Okay, so if I look at my figure, I have along x-axis, it's equal to just 0.9, okay, and along y-axis, it's equal to 1.5. So let us replace, these are the coordinates of E. So I have, for E, it's equal to 0.9 along I, and 1.5 along J, and 0 along K. While for point C, it's simply, for C, it's 0, 0, and 2.25. Now I can replace an MO, okay? So now for the vector moment, as we said, it's moment about O of TCE. So moment of TCE about point O is equal to, I have 2.25K vectorial. Now I replace unit vector. Okay, so I said I take the magnitude 1349 vectorial times unit vector CE. What is unit vector CE? I have 0.9 along I, 0.9 minus 0. So it's 0.9 I. And along J, I have 1.5 minus 0. So plus 1.5 J. And along K, it's 0 minus 2.25. So it's minus 2.25 K. And now, here, it's also easy to do the expansion. No need to do the matrix, because this term here is has only one component. Okay, so if I do the expansion, I can take into factors number 2.25 times 1349, because it's a common factor. So it's equal to 2.25 times 1349 times. Now I have K vectorial I. K vectorial I is plus J. Okay? So it's plus 0.9 J. Now K vectorial J is minus I. So it's minus it's minus 1.5 minus 1.5 along I, and K vectorial K is 0. So this is my result. I deduce that the component of my moment about O has only J and I components. It doesn't have a component along Z. So now I can deduce that what is the moment about x-axis? The moment of my force about X is the component along I. It's equal to minus 2.25 times 1349 times 1.5. It's a negative component, okay? My moment along Y is the component along J. It's positive. It's 2.5 times 1349 times 0.9. And along Z, my moment is 0. Can you tell me, can you expect that the moment about Z is 0? Why it is 0? It is already expected. Who will tell me why?
Because it passes through the origin.
No, because it passes through C, which is on Z axis, okay? We said that if we have a force that is passing by an axis, it cannot produce a moment about this axis. And force TCE is passing by point C, and C is on Z axis. So since we have a common point between the force and Z axis, it cannot produce a moment about this axis, okay? And now, if you want, also, if you do the right hand rule with your hand, you can verify that the component along X is negative and the component along Y is positive. Okay? Any question on this problem? Please ask if you don't understand, I can repeat. Okay, so let us continue.
Doctor, I just have
Yes.
one question.
Yes.
Why did you find it with, why did you find the moment about X, moment about Y, moment about Z? Why didn't you just do the cross product to خلاص?
Because they asked what is the moment about coordinate axis, okay? So they need
yeah.
to know, they didn't just tell find the moment about C. When they say just find the moment about C, you find the vector, okay?
Yes.
Because they said find the moment about coordinate axis, so they are interested in the x-axis, y-axis, and z-axis. This is what.
Okay, thank you.
Now, if you want to look here for the solution, for the vectorial product, they did the matrix method, okay? But here we choose to do the expansion because it's easy, because we have a lot of zeros here. So if you do this method also, you'll get the same results. And as you can see, you obtain components along X, Y, and Z. It's a negative component along I. So here they forgot the minus, okay? Add the minus here. A positive component along J and zero component along K. Okay. Now, another question that might be asked, sometimes we can ask for the moment about any axis. So in the previous problems, I asked for the moment about the coordinate axis, X, Y, and Z. But sometimes they can ask for the moment about any direction, any arbitrary direction. So what to do in this case? We will see here. So we want to find the projection of a moment on an axis. So consider the pipe assembly shown below. Pipe lies in the horizontal plane and it is subjected to a vertical force of 20 newtons. Okay? So we are interested here to find, for example, what is the moment about, let's say, only I-axis. So a simple technique will be first to do the vectorial product, okay? So let's say you are interested in, as we said previously, in X, Y, and Z. So we take the moment about point O, okay? So this is your force F. This is your force F, okay? F is passing by A and it's in the vertical direction. it has a negative component along k. So you replace f by minus 20k. And you are interested to find moment about O first. So you do OA vectorial f. And as can be seen in this figure, the components of OA are along I 0.3i and along J 0.4j. So we can say that moment about O is RA vectorial f equal to 0.3i plus 0.4j vectorial minus 20k. And now, if you do the expansion, I vectorial k is minus, and you already have a minus, so it's plus 0.3 times 20 along j, which will give you 6j. And along I, it is here 0.4j vectorial minus 20k. J vectorial k is plus I, but we have a minus, so it's minus 8i. Now, if I ask you what are the moments about x and y, you will directly say about x is minus 8 and about y it's plus 6. But you can find this in a second method, okay? When you want to find the moment about x, you will say I will take the moment about O and I will do dot unit vector of x-axis, which is I. If you do this dot I, you will get that I vectorial I dot I is 1 and I dot j is 0. So you will end up with minus 8. I will continue this idea in the next session. Okay, so I will open a new session.